In this lesson, we are going to continue looking at exponents and add scientific notation. Next rule for our exponents, we have the power rule. When an exponential expression is raised to a power, the power of each part of the exponential expression is multiplied by that power. So their example in a formula is a to the m power raised to the n power is a to the m times n. And so their example is 4 cubed, and that is squared is the same as 4 to the 3 times 2, or 4 to the 6th power. So let's look at an example that proves that you multiply when raising a power to a power. Here we have 2 cubed to the 4th power, and it's asking us to write it in repeat multiplication. Again, the 4th power out here tells us that what is inside of parentheses is repeated 4 times. So we're going to say we have 2 to the 3rd multiplied by itself 4 times. And the product rule means when we're multiplying with the same base, we can add those exponents. And so our base is 2, and we're adding all 4 of those 3's together. And then 3 plus 3 plus 3 plus 3 is 12. And so we have 2 to the 12th power. And if we were to evaluate that, that would be 4,096. But if we use the power rule, now we say we have 2 to the 3rd power raised to the 4th power. We can multiply those 2, and 3 times 4 is 12. We get 2 to the 12th power. So as you can see, either way you choose to show that, you get the same answer. And with that idea, they're showing us that our negative exponents, when you have -1, it just flips, and then the 1 disappears, but you can have other exponents as well. That we have a to the -m power is the same as a to the m power, and then to the -1 power, or a to the -1 power, and then to the m power. And it wants us to show why a to the -n equals 1 over a to the n, as long as that a is not 0. As we know, we can't use 0 in the bottom of the fraction. So I just wrote it using their symbols. Instead of having the m power, it's the n power. So a to the -n is the same as a to the n power, and that taken to the -1 power. And so we know that the -1 means flip it. So we'll put 1 over, and then our a to the n power, what's inside the parentheses, moves down. Now, there's times where we have more than one factor being raised to a power. And so it's telling us that each part inside the parentheses gets that exponent. So think of it as using the distributive property. Everything inside the parentheses gets what's outside the parentheses. So ab to the nth power is the same as a to the nth power times b to the nth power. And their examples are 2x to the 5th power, the same as 2 to the 5th, and x to the 5th. And then -3x cubed, all raised to the 2nd power, is the same as -3 squared times x to the 3rd power raised to the 2nd power. So again, power to a power, we multiply them and get the 6th power. I notice that we did do -3 times -3 is a +9. And so again, make sure that if you're using powers with negatives, that you put your negative number in parentheses. So the calculator does the right work for you. Let's show an example of how this works. Again, if we show repeat multiplication inside the parentheses, we have 5m, and the 3rd power tells us we're multiplying it by itself 3 times. Now it says use the commutative property and associative properties. Remember, commutative, commute, can move back and forth. an associative, associate, or group together. So they want us to group our 5s together and our m's together, and then simplify. So we know we have our invisible 1s here, so 1 plus 1 plus 1 would equal 3. So we have 5 to the 3rd power. And then for our m's, m times m times m is m to the 3rd power. Notice that it says in our directions and simplify. So that means they want us to take the 5 to the 3rd power and evaluate it. 5 times 5 times 5 is 125. And then we have our m to the 3rd power. So make sure you're following the directions on your Hawks. If it wants you to leave it in exponential form, probably if the number is really big, they'll tell you to do that. Or if they want you to simplify it by actually evaluating it. So if we're using our new property where we get to distribute that 3rd power from the outside in, we will do 5 to the 3rd power and m to the 3rd power. Which still evaluates down to 125 m cubed. So again, we get the same answer no matter how we choose to show the work. And the same is going to be true whether you have the multiplication or division with our quotient. And so we're also going to distribute what's outside into both parts, the numerator and the denominator. And so their example is 3/5 squared. We know it's the same as 3/5 times 3/5, which is 9/25, which can be evaluated as 3 squared over 5 squared. And same thing, they want us to show that. So writing an expanded form, we'll have x over 2 for this problem times x over 2 times x over 2, since we have it to the 3rd power. And if we want to put it in a single fraction, we would have x times x times x for the top, and 2 times 2 times 2 on the bottom. And so that will equal our x to the 3rd over 2 to the 3rd. This time it told us to not simplify, so we're not going to make it x to the 3rd power over 8. We'll just leave it how it is. And for C, they want us to write it and simplify it. So we'll put x to the 3rd over 2 to the 3rd, or again, 3rd power is cubed. And that gives us x to the 3rd over 8. And so we can find that same thing by now using our new property, which shows us that we can distribute that 3rd power in through our parentheses. And so, again, I like to draw my arrows to show that I'm distributing. And that will give me x cubed over 2 cubed, which gives me x cubed over 8. Which is what we expected, because we know we're supposed to have the same thing, since we're proving why our rules work. So here's a couple problems that we're supposed to look at and see if they made a mistake, and if they did, we'll fix it. And so if we take a look at our first problem, we have 2a squared b to the 5th over b squared, and all of that is taken to the negative 3rd power. So the first thing you want to do is simplify inside the parentheses if at all possible. Notice we have b on the top and on the bottom, which when we're dividing, we subtract exponents. So 5 minus 2 is 3. They did that correctly, so we're good there. And so we have 2a squared b cubed all to the negative 3rd power. The next thing they did is they used the -3 in our exponent by flipping it and turning it into a +3. So that's good. And then they distributed. So let's show that distribution to make sure we can get the same answer as what they have. So we have 3 going to the 2. So 2 cubed. The 3 going to the A. The A was already a power of 2, so now we're going to multiply it and make it 2 times 3. And for the B, we had a power of 3 raised to the third power, so we have 3 times 3. So we should get 8, A6, B9. Okay, they didn't do that. What they did is they added instead of multiplied. So their answer was wrong for that reason. Next question, notice we have negative exponents outside the parentheses, so their first step was just to take them and flip them, and they got rid of the negatives, so that's good. There wasn't anything to simplify inside the parentheses to start off with, even though we have x's and y's on the top and the bottom. Since they were to different powers, we couldn't do that first. So now they want us to distribute. So let's take a look at that. We have the third power going to the 6th, and 6 to the third power is 216. So that's okay. Third power goes to the -1 on the x, and -1 times 3 is -3, so they did that right. And the y has the invisible 1 times 3 to get third power. So the top, they did okay. Let's check the bottom. We're distributing the 2, so -3 squared is -3 times -3, which is +9. Oh, they made a mistake there, which if you don't put parentheses in the calculator, it'll tell you it's -9. Then 2 times 2 will give us 4 for the new exponent on the x's, and -1 times 2 is -2 for the exponent of the y's. So other than the positive sign needing to be there instead of negative, then we're good. So now when we simplify our last step, remember we'll take our 216 over 9 and simplify. For our x, we're taking our top exponent of -3 and subtracting off our bottom exponent of 4. And for our, that looks like 47. I'll just put -4 without the parentheses. For our y, we have the top exponent of 3 minus the bottom exponent of -2. 216 divided by 9 is 24. -3 minus 4 more gives us -7. And 3 minus -2 is the same as 3 plus 2, which gives us 5. So comparing our answer with theirs, again, fixing the negative to a positive, we have 24. Since x was -7, they put it in the denominator and just wrote 7th power, so that's good. That's the correct way to write that. And y to the 5th is positive, so it stays up with the 24. Again, the only mistake on that one was a sign error. Okay, let's take a look at scientific notation now, and it's using these rules that we looked at when writing them. Scientific notation is a way to write really large numbers or really small numbers as a power of 10. And especially when there's a lot of zeros, it helps to make sure that things don't get lost in translation, so to speak. Remember back when they were dealing with numbers and things, they didn't have calculators or computers and things like that. So everything was done by hand. So it was just a way to make sure that they weren't losing some zeros along the way. And so this definition sounds kind of tricky. It says a positive decimal number written in scientific notation has the form a times 10 to the nth power, where 1 is less than or equal to a is less than 10, and n is an integer. So the value of a has to be between 1, and it can be 1 and 10, but it can't be 10. What that means is you're allowed to have 1 digit in front of your decimal, and it can't be 0. And then n is an integer. Remember, integers are just positive and negative counting numbers. And so when you write a number in scientific notation, you have to decide where the decimal is supposed to go and count the number of places that it was moved, and then show how many times you moved the decimal with your power of 10. And so when I think of numbers, I think of money as much as possible to help me. And let's look at an example in number 7 so we can see what happens when moving that, because hopefully this will make more sense when you see an example. I've already mentioned that it's used to write small, big numbers, but it says that the distance from the Earth to the Sun is 149. Let's see here, we have millions, billions, 597,870,700 meters. And so let's just stop and take a look at that number and write it in scientific notation. So 149,597,870,700. So in this number, there is no decimal place written, so we know it's at the end. We need only one number in front of the decimal that's not a 0. So the first number that we have in our number that is not a 0 is the 1. So that's where we need the decimal to be. And if we write the number with the decimal there, we would have 1.4995978707. And any extra zeros at the end can be dropped off. Those are called terminal zeros now. They're not needed when they're at the end. And so now, for our power of 10 times 10, we have to show how we wrote that number. The decimal was here at the end, so we're going to move the decimal 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We moved 11 spaces. We're going to use 11 as our exponent. Now, to be able to distinguish between a really large number that started off with and a really small number, that's where we use the integers or positives and negatives. When I look at that 149 plus billion, I say, yeah, I'd like my bank account to be that. So it's a big number, it's a good thing. So we're going to use a positive exponent on our 10. But if we look at the radius of a carbon atom, this is a pretty tiny number here, and that's going to be a bad thing. I do not want my bank accounts to look like that, so we're going to use a negative exponent for there. So we have 0. Let's count how many we have. 1, 2, 3, 4, 5, 6, 7, 8 zeros after the decimal. 1, 2, 3, 4, 5, 6, 7, 8 zeros, and then 7, 7, 2. So again, we see our decimal way up front. We need it to be after the first non-zero digit. So if we look at this, the first number that's not a 0 is that first 7. So that's where we need it to go. And if we look at that number that we just created, all those zeros up front, we aren't going to need anymore, so they'll disappear. And we have 7.72 that we created. And so now we need to show how to get there. So by our 10, and we'll move our decimal 1, 2, 3, 4, 5, 6, 7, 8, 9 times to get it to where it is. So we'll show that by -9. So again, we moved the decimal to make the number bigger, so it started off small, which is a bad thing. And so that's why we use our negative exponents, how I think of it. And then if you were asked to go backwards and looking at a scientific notation to a regular number, let's do 2.3 times 10 to the 5th power. That 5 tells us how many moves, not how many zeros to add. So we have our 2.3, and we're moving 5 times. It's a positive, so our number is going to get bigger. 1, 2, 3, 4, 5 times. And now we fill those spaces that we don't have numbers in with zeros. So notice we added 4 zeros. And if your decimal point was even longer, like 2.587 times 10 to the 5th, notice we have 1, 2, 3 moves to get after, so the 4th and the 5th move would need to have 0. So 2, 5, 8, 7, 0, 0 would be that one. So again, you can't count the number of zeros with that exponent. You have to count spaces or moves to be able to move the decimal and get an appropriate spot. Let's say that we had 2.3 times 10 to the -5 power. So again, negative's bad in my checkbook. So I have to make the number smaller. So we're going to move to the left. Notice since we're going left with our negatives, there's only going to be one number in front to move because that's the definition of proper scientific notation. And so we're going to add 4 zeros to be able to move spaces. So you're always in the negative going to add one less zero than the number that you see. We see -5, so we're going to add 4 zeros. Again, because we'll only ever have one decimal in front or number in front of the decimal. That would work. And so our decimal place is here. Okay, so if you're asked to go from scientific notation to write it as a regular number, you'll know what to do. Now, if you're multiplying or dividing using synthetic notation, you're going to use the same rules that you've used before with your coefficients. Think of your number A or number B in this scenario as your coefficients. You're multiplying those or dividing those, and then adding or subtracting the exponents, just like we've been doing in other types of problems. And so we'll look at some examples, and see if these are done correctly, and if not, we'll fix them, and we can walk through the process while we do that. And so again, our numbers up front, again, just like a algebraic expression, think of it as kind of like your coefficient, those front numbers. They get multiplied in the multiplication problem, so 12.5 times 5, and that gives us 12.5. And then when we have multiplication with our exponents, we're adding them. So I wish they would have written this as 10 to the 4 plus -2. And when we add those, we do get 2. So that checks. But notice they still have another answer here because our 12 has 2 digits, and that's not proper scientific notation. So we had to move that decimal in one time to get it to where it needs to go here. And again, 12 is better than 1.25. It was a good thing. And so what they did was they added 1 to our exponent to show that extra move there at the end. So that's why the answer is 1.25 times 10 to the 3rd power. You always have to write your answer in proper scientific notation form, just like no negatives on your exponents, only one digit in front of your decimal for scientific notation. That is not 0. Okay, let's look at our second one. Here's a division problem. So in the division problem, we're going to divide our front numbers. 5 divided by 4 is shown here, which is 1.25, which is good. And then we're supposed to subtract our exponents, -2 and -5. And so again, I wish they would have done it like this and used our rule that way, that we can divide by subtracting. And -2 minus -5 is the same as -2 plus 5, which equals 3. So it should have been the third power. What they did is they added them together, and we can't add them in division, we have to subtract them. So 1.25 times 10 cubed is a proper way to write that. Okay, here's a chance for you to work some problems through. And notice that in 16 and 17, they want you to write each number in scientific notation first and then perform the operation. So if that was a quiz or a test problem, you would have to make sure that you included all of that. Otherwise, you would lose points. We haven't had a whole lot of examples using all this good stuff here. So let's actually look at number 15 together. For 15, we have a lot of stuff going on, and so we'll look at how to tackle the problem, what to do first, and things like that. Okay, if that just jumped on the screen for you, I paused the video while I wrote that out so you wouldn't have to wait for me to catch up with you. But if you notice all these parentheses, there's only one thing that has to be done outside the parentheses, which is our 2. Otherwise, these parentheses are meant to show multiplication. But we do have this 2 to distribute first. So let's leave our 5x squared alone, and we're multiplying it by 3 squared, which is 9. And x, 2 times -1 would be -2. And that's going to be over our 25y cubed times our 6y to the -2 power. Now you might be tempted to move those negatives to the other side, but let's simplify first before we start moving anything. So again, when we simplify, we're going to do 5 times 9. And then we add exponents. So for our x, we're going to have 2 plus -2. And for the denominator, we have 25 times 6. And for our y, we have 3 plus -2. Okay. Then 9 times 5 is 45. And then 2 plus -2 is 0. Remember, anything to the 0 power becomes 1. So we can just ignore that because anything times 1 stays the same. So we'll just get rid of it. And that is over 25 times 6. Well, 6 quarters would be $1.50. So we have 150. And our y, 3 plus -2 is 1. Which again, our 1 isn't necessary, so we can just ignore that as well. So now we need to simplify. 45 over 150 simplifies down to 3/10 because we can divide both of those by 15. The x is now gone. The y does not have a negative exponent, so it gets to stay right where it's at. And so there's our answer. So I want you to pause the video and work on the rest of these, and then check your work, and when you're ready, move on to the story problems. A scientist calculated that her experiment consumed 520,000 joules of energy. She wrote it as 52 times 10 to the fourth power. Did she do it correctly? If not, which she didn't, what should it be? So hopefully you realized that 52 has more than one digit, so it needs a decimal place in it. So again, it's back here. We need it to be in between. So we'll show that move by adding 1 to our exponent. So it should have been 5.2 times 10 to the fifth power. A molecule of table salt weighs approximately 9.704 times 10 to the negative 23 grams. What would be the weight of 4 million molecules of table salt? So 4 million in scientific notation, well, there's only one number that's not a 0, which is 4, so it would go after. And we have 6 times to move 3 to these 3 zeros, 3 more. So it'll be times 10 to the 6th power. And so write an expression to find the weight of 4 million molecules of table salt. Well, here we have to multiply. Okay, so we have a molecule of table salt weighing approximately 9.704 times 10 to the negative 23 grams. And it's asking us what would the weight of 4 million molecules of table salt. So first, 4 million in scientific notation. And we know the decimal place, if it's not there, is understood to be at the end. The first number that's not 0 is 4, so we need a decimal to move up to after the 4. And 4 is all we need because all those zeros will drop off. And to show how many times the decimal moves, we have 3 to this come and 3 more, so it'll be the positive 6th power. And so to find the weight of 4 million molecules, we'll take our 4 million, so 4 times 10 to the 6th power, and multiply it by the weight of 1, which is 9.704 times 10 to the negative 23rd power. So to simplify it, we'll take our front numbers here and multiply them together. And then for our exponent, we add exponent, so times 10 to the 6 plus negative 23. When we do that, we get, I'll write it under here, 38.8816 times 10 to the negative 16. And again, we need to change it in proper notation by moving the decimal place once. And then we'll show that by adding 1. So our final answer is 3.8816. We have too many 8s up here. So let me erase this whole thing. Sorry. 38.816 times 10 to the negative 17. And again, we'll move it in 1 and show that by plus 1. So 3.8816 times 10 to the negative 16 power. And so what does this answer? And write it in a complete sentence. I'll just say it. The weight of 4 million molecules of table salt weigh 3.8816 times 10 to the negative 16 grams. Let's look at one more example. An astronomical unit, or AU, is defined as the furthest distance the Earth is from the Sun. The value of 1 AU is 150 billion meters. And so write that in scientific notation. And we can see it 1 first, so we'll do 1.5 times 10, and let's count by threes to see how we get there. 3, 6, 9, then 10, 11. So 1.5 times 10 to the 11th. The furthest distance that Mars orbit takes it from the sun is approximately equal to 200 billion meters. Write this in scientific notation so we see a 2 and nothing else. Times 10, and again we have 3, 6, 9, 10, 11. So we use this to find about how many AUs is that. And so to do that, we have the distance, 2 times 10 to the 11th, divided by the amount of AUs, that is equal to 1.5 times 10 to the 11th. And when we do that, we'll do 2 divided by 1.5 times 10 to the 11 minus 11. 11 minus 11 is 0. Anything to the 0 power is 1, so we know that drops off. And so rounding to the nearest hundredth, 2 divided by 1.5 is 1.3 repeating, so 1.33 AUs. Light travels at the speed of approximately 2 times 10 to the negative third AUs per second. Determine approximately how long it will take the light to travel to Mars when it is the furthest from the sun. Well, for this one, we have our 1.33, and we're dividing it by 2 times 10 to the negative third. Well, I'm just going to go ahead and change that to a decimal. First, because it's easier, but I'll show you the other way as well. So 1.33 divided by 0.002, again we had to move that decimal back 3 spaces, which gives us about 665 seconds. Otherwise, we can do it using the scientific notation way. And to do that, we would divide 1.33 by 2, and then it's times 10. Remember, there's technically 10 to the 0 power up there, minus our negative 3. And if we do 1.33 divided by 2 in the calculator, we get 0.665 times 10 to the third power. And writing it in scientific notation, we know would move it over 1 decimal place, and it's smaller, so we're making it bigger. So we would take away 1 instead of adding 1, and so that would be 6.65 times 10 squared, written technically in scientific notation, but normally we don't talk about seconds in scientific notation. So if we go ahead and move it those last 2, we would get our 665 seconds. That way. Okay. So if you have any questions while you're working on your homework, let me know. Otherwise, I'll see you next time.